Finally, we were asked to show, using the Cauchy-Schwarz inequality, that this inequality holds true. So as with any Cauchy-Schwarz inequality problem, really what the problem boils down to is picking vectors u and v such that when we plug them into the Cauchy-Schwarz inequality, it tells us something about the inequality we are asked to prove. What's the Cauchy-Schwarz inequality? Well, let's remember, it says that if u and v are two vectors in Rn, meaning they have the same number of components, then the inequality is that the absolute value of their dot product is less than or equal to the product of their lengths. Okay, so my claim is that all this problem really boils down to is picking good u's and v's, well, not plural, picking a good u and picking a good v such that when we plug those into here, we'll get something useful to our situation. Let's try that. And maybe just to save some space, I'll write u and v a little further to the left. Now, that's the question. Like, what am I supposed to put in u and what am I supposed to put in v? What I notice in the inequality I'm asked to prove is that somewhere I have a sum of the square roots of my y's. And over here on the right, I have y bar, but y bar is really just 1 over n times the sum of my y's. So on both sides, I have a sum of y values involved. And I know that when I find the norm of a vector, so like the norm of u here, is going to involve taking the square root of the components of u squared. Sorry, the square root of the sum of the squares of the components of u. So over here on the left, I have things that have a square root on them, and over here on the right, I have things that don't have a square root on them. And this sum seems like it came from squaring the individual things in this sum. So how do I make the connection? Well, one idea is to say, well, why don't I put the square roots of my y's in one of the two vectors? Let's just say put it in u. Okay. What do I put in v? Well, many students may often think, why don't we just also put the same thing in v? Let's just try it out, see what happens. Okay. Let's just plug both of these, plug this u, plug this v into the inequality and see what it gives us. Well, on the left, we're going to have the dot product of u and v. Well, what does that give us? U dot v is going to be the square root of y1 times the square root of y1. So it's going to look like the square root of y1 squared plus the square root of y2 squared all the way through the square root of yn. Oops. Squared. That is all less than or equal to the length of u. What is the length of u? That is going to be the square root of this thing squared plus this thing squared plus dot 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 plus this thing squared. So why don't we try that? Square root of that squared plus square root of that squared. But then here we realize that u and v are the same thing, and so the length of v is going to be that same thing too. And we look and simplify and realize that all this is saying here is to add up the y's. y1 plus y2 plus yn. And all this is saying, since we have the same thing being multiplied, the square root is being multiplied by itself, so we can drop the square root there. All this is also saying is y1 plus y2 plus yn. So this is saying the sum of the y's is less than or equal to the sum of the y's. I already knew that. I didn't need the Cauchy-Schwarz inequality to tell me that. And this is the result you're going to end up getting anytime you make u and v be the same vector, right? In order to really unlock some insights from this inequality, we're going to have to pick a v that is different from our u. Okay, but this is a good place to start. And again, I'm trying not to just leap straight to the solution. I'm trying to think through how one might in an exam. Okay, so here's the key insight, and there are some practice exam problems that may guide you to this insight. It's the fact that when you take the dot product of any vector with another vector who's made up of only the number 1, the effect of that dot product is the sum of the other vector. That is the sum of the vector that isn't just 1, 1, 1, 1, 1. Let me show you what I mean. If I take the dot product of 2, 3, 4 with 1, 1, 1, the result is 2 times 1 plus 3 times 1 plus 4 times 1, which is just 2 plus 3 plus 4. What happens if I employ that principle here? And this is a common Cauchy-Schwarz inequality strategy. Let's test it out. On the left, I'm going to have the dot product of u with v. That's going to be the square root of y1 plus the square root of y2, dot, 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 plus the square root of yn. And I'll add some coloring here just so we know which piece of the inequality this is coming from. Maybe we'll say that this is the green part. So I'll have root y1 plus root y2 plus root yn is less than or equal to the length of u. What is the length of u? To me, that looks like the same thing we had before, which is the square root of this thing squared plus this thing squared plus this thing squared. Times the length of v. What is that? Well, it's the square root of 1 squared plus 1 squared plus 1 squared. So the Cauchy-Schwarz inequality got us this far. It's saying, hey, you picked a u and v, and the consequence of that is that this inequality must hold. Well, what can we simplify from here? Because this is starting to get us in the right place. Let me write this in one line, and then we may have to move some things around to simplify here. On the left, so that is up here, I have the sum of the root yi's. And on the right, I have the square root of the sum of the yi's, because the square root gets dropped here. So I might write this like this. And what do I have here? Well, 1 plus 1 plus 1, n times is n. So this is the square root of n. Good. I'm actually almost there. Now what can I do? Well, here I notice the sum of the square roots is squared. A lot of squares and square roots here, but this thing is being squared, and this thing doesn't have a square root on it. So what this seems like is I need to square both sides. And why is this a legal operation? Because it's not always a legal operation. It's legal because I know this thing can't be negative because it's the sum of a bunch of square roots, and square roots can't be negative. And these also can't be negative because the square root of n is an integer, it's the number of data points you have. A positive integer is the number of data points you have, can't be negative. And similarly here, this is the square root of something, and so that square root can't be negative. Okay? The reason I bring that up is that in general, it's true that -3 is less than 2, but you can't square both sides here and still get a valid inequality because it's not true that 9 is less than 4. So it matters that both sides here are for sure not negative. Okay, but because they're not negative, I can square both sides here. What does that buy me? Well, squaring both sides, where'd my eraser go here? Squaring both sides allows me to drop both square roots. So now I have this and this. And this n is a constant, so I can pull it out of the sum. Is this the same thing as what I've got going on up there? Not quite, but it's almost there, right? All I need to do to make the conversion, this may seem like it's coming out of nowhere, but now I'm allowed to do whatever I want to do to this inequality as long as what I do is valid. I just need to do a little bit of massaging here to get this form exactly. All I need to do is divide both sides by n squared. Totally legal move as well, but when I divide both sides by n squared, or multiply both sides by 1 over n squared, that allows me to put a 1 over n within the parentheses, because everything within the parentheses is being squared. That's perfectly legal. This 1 over n squared here is out of the parentheses. And over here, this becomes 1 over n times the sum of the i's, which is y bar. And that's it. That's what we were asked to prove. So that's how I might use the Cauchy-Schwarz inequality to prove this. Now, something that a few students thought of that I didn't initially think of was you can avoid having to do all of this engineering with the n's afterward if you just put not 1's in this v, but you put 1 over n's, which is clever. Again, I didn't think of this. But if you do it, this all just falls out with one step, I'm pretty sure. So let's test it out. What is the dot product of u and v? Well, this looks like to me root y1 over n plus root y2 over n all the way through root yn over n. Looks good. And that's going to be less than or equal to the length of u, which we've seen before, square root of y1 plus yn times now the length of this new v vector, which is different. It's going to be the sum of these things squared. So that's going to be 1 over n squared plus 1 over n squared, 1 over n squared. Let's simplify a little. what is this business up here on the top? This to me looks like 1 over n times the sum of the root yi's. What is this thing? Root the sum of the yi's. And what is this thing? In the sum here, I have 1 over n squared being multiplied through n times. So this is actually, in here, without the square root, n over n squared, which is 1 over n. So this is the square root of 1 over n. Now all I got to do is just square both sides and we're done. Because when I square both sides, which again is legal by the logic I used before, well, I'm done. Because when I square both sides, the left side looks exactly like the left side of the inequality I'm trying to prove. And on the right side, squaring both sides allows me to drop my square root here and drop my square root here. And I'm done. This is exactly what I was asked to prove. The 1 over n was up front, but doesn't matter. It's a constant. I can write it wherever I would like, and we're done. So if you picked your v even more cleverly, the inequality would fall out even quicker. Now you may say, well, I didn't think of these u's and v's in the exam. How might I do this in the future? And the truth is, this requires a little bit of educated guesswork, but the nice thing is that there are only a few possible patterns for these types of questions to follow. And now that you know this one, which also appeared in some of the past exam questions, you're well equipped to tackle similar problems in the future. So in general, this trick of dotting a vector with ones, giving you the sum of the other vector, that's like something to remember just in general moving forward.